Let's do another example problem using Newton's laws of motion. In this problem, let's talk about friction forces. In the last lecture, we talked about tension forces. Here we'll deal with friction forces. But you're going to notice that the procedure we're going to use is the same as the procedure in the previous problem. Okay, so here's the problem. First of all, let me just define what I mean by a friction force. A friction force is a force that one object exerts on another object. That one object exerts on another due to contact. Okay, due to contact, but in particular, it always acts parallel to the surface. It always acts parallel to the surface, separating the bodies, and attempts to prevent the motion, relative motion of the bodies. Attempts to prevent relative motion. Okay, so for example, if you place a box on a floor and try to slide the box along the floor, the friction force is exerted by the floor on the box, and it acts parallel to the floor in the opposite direction you're trying to move it. So if you're trying to slide it eastward across the floor, the friction force would be pointed westward along, it'd be acting on the box in the westward direction. Okay, so notice that the friction force, like the normal force, is a force that two bodies, that one body exerts on another body, but whereas the normal force is perpendicular to the surface, the friction force is parallel to the surface. Okay, there's a formula for a friction force. So the friction force, let's denote it by the letter F, and you can calculate the friction force if you know two things. So this is the formula for friction force. Friction force. Mu is called the coefficient of friction. It has to do with the roughness of the material. So the rougher the material, the larger mu, or the coefficient of friction. So for example, if you have a surface that is ice, it's going to have a relatively small coefficient of friction. If it's Velcro, it's going to have a relatively large coefficient of friction. N here is the normal force. So the friction force and the normal force are related to one another. So the normal force is the perpendicular force with which a surface pushes on another. And if you multiply that by mu, you will get the friction force that attempts to prevent relative motion of those two objects. Okay, so let's do an example problem here. So let's go back to our ramp. We talked about ramps before in the context of Galileo, but let's go back to the ramp problem, and now we're going to use Newton's laws of motion to analyze this situation. So suppose we have a block that is on a ramp. The ramp has an angle theta. Let's say the block has a mass m. And I'm going to leave these general. This could be 45 degrees or 30 degrees or whatever. I'm just going to call it theta for now, and this mass, I'm not going to specify this either. Okay? All right, now here's the question that I want to ask is, how big must the coefficient of friction mu be in order to prevent slippage? So in order to prevent the mass m from sliding down the ramp. This is a pretty straightforward ramp problem. Okay, so how do we solve this problem? As always, what we want to do is follow our procedure, which starts by setting up a free body diagram for that mass. Okay, so let's denote the mass by a dot, and now let's identify all of the forces that are acting on this mass. Okay, so let's start with the easy one. First of all, it's got weight. Okay, so here's the weight pointing downward. There's also a normal force that with which this ramp is pushing up on the block, and it's kind of at a funny angle. So I'm going to draw the normal force like this Okay, it's perpendicular to the surface, so it's going to have an angle, whatever angle theta is here, that's the angle that this normal force is going to have with respect to the vertical as well. What other forces are acting on it? Well, if the block tries to slide down the ramp, the friction force that the ramp exerts on it is in the opposite direction, so it's kind of up the ramp, and it's parallel to the ramp. So notice that the friction force and the normal force are going to be at right angles to one another, because that's applied parallel to the surface, that is perpendicular to the surface. Okay, so there we have it. We have our free body diagram. The next thing we want to do is set up a coordinate system and write down Newton's laws of motion in that coordinate system. Okay, now here I mentioned before that we're going to work primarily with Cartesian coordinate systems. We're going to work with the Cartesian coordinate system once again here, but here we're not going to have the Cartesian coordinate system oriented perfectly vertically, that is with y along the vertical axis, because our problem can be simplified by drawing this xy coordinate system at kind of a funny angle. So I'm going to draw it right on my free body diagram. Let's call this direction the x direction, and we'll call the vertical direction, by vertical now I mean, well, it's the direction perpendicular to the surface of the ramp. So that is the coordinate system we're going to choose, and the reason I'm choosing it this way is because it makes our Newton's second law calculations a little bit easier, because we have this force is strictly in the y direction and this force is strictly in the x direction. The weight now is going to have a component in the x direction and a component in the y direction. So let's actually just do that right away. Let's decompose the weight into two components. So this would be the weight in the x direction, and this would be the weight in the y direction. Okay? All right, so now let's write down Newton's second law, and let's do this in component form. So in the x direction, well, the sum of the forces in the x direction are going to be equal to the mass times the acceleration in the x direction. What are the forces in the x direction? Well, you've got the weight in the x direction, W sub x, and then you've got the friction force, which is in the negative x direction. So I'm going to put a negative sign right here, and then any numbers I get are going to be positive numbers for the friction and the weight in the x direction. And that is going to be equal to the mass times the acceleration in the x direction. There we have it. That's Newton's second law in the x direction. What about in the y direction? Well, the sum of the forces in the y direction are going to be equal to the mass times the acceleration in the y direction. Now, what are the forces in the y direction? Well, you've got the normal force, which points vertically up along the y-axis, and then you've got the weight in the negative y direction, so negative W sub y is going to be equal, oops, I messed this up. Let me get my eraser out here. Oh, that's a big eraser. Just a minute. I think my daughter's been playing with this, which is just fine. Let's erase this right here. This should have been the acceleration in the y direction. Sorry about that. Okay, mass times acceleration in the y direction. There we have it. We have Newton's second laws written in component form. Okay, now step 3, we're going to apply any constraints. Well, we know let's just list them. The acceleration in the y direction is going to be 0. That is, it's not accelerating vertically, that is perpendicular to the ramp. It's going to be resting or constrained to lie on the ramp the entire time. Another constraint we're going to have is we're trying to solve for how big must mu be to prevent the mass from sliding, right? So we're going to demand that the acceleration in the x direction is 0. That is, so it's not sliding. So that's another constraint. All right. What else do we know? Well, we know that this angle right here is going to be theta. You can see that from geometry if you're careful with this, which means that this angle right here is also going to be theta. Okay, and that's going to allow us to write Wx and Wy in terms of the weight and the angle theta. So in particular, Wx is going to be W times sine of theta, and Wy is going to be W times cosine of theta. If you don't see why this is, you might just think about sine of theta is opposite over hypotenuse, and so you can solve for the opposite. Wx would be W times sine theta. That's how I get these. So we're going to express the weight in terms of, the weight in the x direction in terms of the weight and the sine of the angle. Okay? All right. And now these are all the constraints. Let's apply these constraints. So let me go over here. So when we apply these constraints, what's going to happen to our x direction force? Let me get rid of this. It's going to get in the way. The x direction equation of motion is going to be written like this. Let's plug in, oh, by the way, let's just say W equals mg. We know that also. All right, so going back to here, the weight in the x direction would be mg sine of theta minus the friction force, which is going to be, let's right away plug in that as mu times the normal force. That's the relationship between friction and the normal force, and that is going to be mass times the acceleration in the x direction, which we know is going to be 0. All right, and so we can solve this right away. Well, not exactly, but let's write it this way. Let's rearrange this to be mg sine of theta equals mu times the normal force. Okay, so that's our x equation. What about our equation for the y direction? Well, the normal force N minus the weight in the y direction would be minus mg cosine of theta, and that is going to be equal to the mass times the acceleration in the y direction, which we know is going to be 0, so we can write this as N equals mg cosine of theta. So notice now that I have these two equations. N is mu times the normal force is mg sine theta, and N is mg cosine theta. The nice thing now is that we can combine these two. By the way, we're doing step 4, in case I didn't say that. We can combine these two equations. In fact, we can divide this equation by this equation. So let's divide the x equation by the y equation. You'll see why I'm doing this in a moment. So let's take mg sine theta equals mu times the normal force, and we'll divide both sides by the same number. That it will divide by mg cosine theta, and we'll divide this side by n, because those two are equal to each other, so we can divide both sides by the same number. This is nice because the mg's go away, the n's go away, and voila, we have that the coefficient of friction is sine theta over cosine theta, or if I rearrange this, mu is equal to tangent of theta. In other words, in order for this block to not slide down the ramp, the coefficient of friction has to be numerically equal to the tangent of the angle. So for example, as an easy case, if the angle theta was 0, if it was on a horizontal surface, tangent of 0 is 0, you could have a coefficient of friction of 0 and it still wouldn't slide, which kind of makes sense because the block is sitting on a horizontal surface. But as theta gets larger and larger, as it approaches 90 degrees, the coefficient of friction has to get larger and larger in order to make the block stick to it. Okay, and tell you what, why don't we stop there, and I'll probably say a few more things about this problem before doing another example problem.